Hi, guys, and welcome to the Trial Site News podcast series. I'm Dr. Erin, your host, and today we have Dr. Denise Kirschner with us, joining us from her car. So we're glad to catch you when we can. And she is at the University of Michigan Medical School. She is a math biologist who heads Michigan's computational immunobiology of tuberculosis lab. That was a mouthful, sorry.
It is.
And we're going to talk about a first of its kind whole lung simulator for tuberculosis, which it's kind of a fascinating topic and really neat. I think you guys will like it. But first, Dr. Kirschner, do you mind just telling us a little bit about yourself and what you do?
Yeah, sure. I think context is everything. So I appreciate the opportunity to be here and to tell you a little bit about me, and then sort of how we got started on this work and where I am. So, I'll be honest with you and tell you that biology has been, something that has driven me my whole life. Been really interested in it. I always wanted to go to medical school, and but I was good at math. And in my generation, there weren't too many women who were in math classes or good at math. Usually, sometimes I was the only one. In college, in fact, I was the only woman in calculus 3 as a freshman, and then I got the hundreds on the test. So I've always been an enigma because of that. And my professors actually approached me at some point and said, you might consider getting a PhD instead of going to medical school and getting an MD. And I'm like, well, what would I do with that? And so here I am, all these years later, able to apply mathematics to study diseases. So in a medical school. So I really came full circle. And so the idea is that, there's lots of important questions, open questions in biology, in medicine, in infectious diseases, and some of them don't have good techniques to approach. And so providing a computational approach is really another way at getting at these really complex problems. Sometimes experiments can't even be done. So for example, to study tuberculosis, there are people that do mouse studies, but mouse work doesn't really get at the core of TB because mice don't actually get TB the way humans do. So we use a non-human primate model. We have a colony of 300 monkeys that are housed at the University of Pittsburgh because they have a very large animal biosafety level 3 facility. So we can do some studies, but again, your sample sizes are going to be small. You can't do hundreds and hundreds of monkeys in a study, right? Just like you wouldn't with humans. And so there's a lot of complications. So the modeling brings in a piece that helps you narrow the design space, the study space for whatever problem is that you're interested in, whether it's vaccine development, drug studies. And so to do anything like that, the first thing you need to do, of course, is to build the model that you believe in, that you can run through the gauntlet and make sure that it passes all the tests so that you can use it then to address questions of interest that are currently not easily tractable in the scientific setting. So I hope that gives you a little context and background.
Absolutely. Fascinating background there. So let's talk about tuberculosis before we dive into the whole lung simulator that you and your team created. What are some of the challenges, the current challenges regarding tuberculosis that you hope to solve by creating this whole lung simulator?
Sure. So I think most people don't understand the global impact of TB. So we all are familiar with COVID, so I'm going to use that as our example. In the past 2 years, 2 million people died of COVID disease each year. And probably for the past 50 years, 2 million people have died each year of TB. So while we think COVID was a huge world health problem, and it certainly was, TB exceeds it by far because it's been around since Egyptian times. We find Egyptian mummies with tubercles in their lungs. So it's a very old disease, and yet it has been with us in endemic form, and there are times when it becomes pandemic form, and that happens, for example, at the onset of HIV in the world. HIV is immunosuppressive, and so people that have latent TB, and I'll talk about that in a second, can reactivate their disease, and so that is highly spreadable, just like COVID. And speaking of COVID and TB, they're both transmitted the same way. Someone coughs or breathes, sings, and you breathe it in. Now, a couple of differences. One, COVID is a virus and TB is a bacteria. So that is extremely, very different because it's actually a living organism where viruses are not. The other thing is to get COVID transmitted, it could take up to 1 billion viruses that need to be transmitted in a droplet that you would inhale. With TB, it might be as few as 1 bacteria. And that's really surprising because most bacterial infections, like if you get food poisoning at a restaurant, you've probably got 1 million bugs that you ingested. So it usually takes a very high burden. That's not the case with TB. Very low infectious dose. So we have something that's very low infectious dose, spread as easy as something like COVID. But it hasn't been that common in the Western world. We don't see a lot of it in the US and the UK, and that's mostly because of good, quality of life, good nutrition, good living conditions, those kinds of things. So it's endemic in places that are highly dense, poor sanitation, poor, living conditions, poor nutrition, that they seem to go hand in hand. And a lot of times it's because people are packed together on a bus going to a mine in Africa or, in Mexico City, and so you see it in endemic in places like that. But we do have TB in the US. It's actually on the rise in the US. So it is becoming again on the radar of healthcare professionals here. So what's the problem with studying? What are the difficulties of studying TB? The main thing is that it sets up its story in the lungs, and it's only in the lungs. So everything's happening in the lung environment. The lymph nodes, which are, your sites of generation of immunity, there we have 700 of them in our body. That's why the doctor feels your neck, when you go to the doc, to see if you're draining from your nose or your throat. Well, in the lungs have draining lymph nodes and that are providing immunity for the lung environment if there's infection there. And of course, blood is how these cells move around between the lymph nodes and the organ of interest, which in this case is the lung. So that's one very difference, because COVID is a very systemic disease. It's sort of throughout your whole body and the whole blood, where it's very localized in your lung. But we don't like dissect people's lungs or, sample people's lungs. That's not something you can do. So it makes it very difficult. We can take blood, but blood has been shown not to really be a good reflection. Like if you have certain diseases and they draw your blood, they can say, oh, she's got heart disease because, this is high and this is high and this is low, but with TB, that's not a possibility. So the only way to do it is to get an animal model that can help us really understand, what is going on during infection and how to make predictions about treatment or vaccination and these kinds of things. So the monkey model, as I mentioned earlier, is really the best model for that. But there are many limitations.
Sure.
And so we step in with our computer models, and we've been doing these models for about 25 years now. We started first looking at this thing called the granuloma that forms in the lung. So it's just like the way, should I stop and let you ask me a question? Maybe?
I just wanted,
Yeah.
it was very good explanation. I just wanted to jump in.
I'll just keep going. So you jump in. Yeah, sorry.
No, don't apologize. A lot of people know that there's a tuberculosis vaccine out there. And so I wanted to ask you to elaborate on that, as well as the granulomas and pulmonary TB, or in the lung. Pulmonary means in the lung, specifically, and what the effectiveness is there, because that kind of relates to what you guys are doing, I think.
Exactly. So it is interesting that there is a vaccine for TB. It's called BCG, which stands for Bacille Calmette Guérin, which is a live vaccine of a broken cousin of TB. So they make a version of the bacteria that's not quite as healthy, and we give it to people. And the idea is that it's supposed to protect you. That's the way the polio vaccine worked as well, which was actually quite effective. But for TB, it's actually not as efficacious. And we know that it's somewhere between 0 and 80% effective. And that's a pretty wide span. And obviously, since we vaccinate most of the world, and 2 billion people right now have TB. So we're talking 1/3 of the world are positive for TB. So obviously, it's not that protective. And now, of those people that have TB, 90% of them have latent, which means that they have clinically controlled it. But there's actually stuff going on within the lung, within these granulomas, which I'll speak about in a second. But the people the 10% that have active disease, that group, if they're not treated, they will die within a year of it. And again, these people that have latent can reactivate because of things like HIV, immunosuppression, and or malnutrition, even aging. Over time, your immune system is not as effective, and all of these things can reactivate latent disease, which again allows you to spread it. You're not able to infect anyone if you have the latent form, of the clinically latent form. That means everything clinically is sleeping, including a chance for transmission. So what happens when you do transmit? So if you and I are in a room together and I cough and you breathe in, 10 bacteria from me, each one is going to land in your lung like a grain of sand inside of an oyster. And it is going to form a granuloma, which is basically the immune response's version of a pearl. And it basically says, I can't get rid of this thing because it's had so many swings at the evolutionary with the immune response being around for thousands of generations with humans, that it has evolved a way to circumvent the normal cells in the lung that would eat it up, chew it up, and get rid of it. And so these granuloma form, which are just collections of immune cells, because once this bacteria is taken up inside of these cells in your lung that are called macrophage for big eater, that's all they do all day is they eat up stuff and they spit it out. But for some reason, mycobacteria has figured out ways to survive and actually multiply with inside of these macrophages. So they're kind of a wolf in sheep clothing. And then eventually that macrophage will burst open. More macrophages will come in, take the bacteria up. And so this granuloma begins to form. And it actually almost looks like a tumor because it's a collection of immune cells that are forming around to physically constrain and immunologically contain the bacteria. So basically I can't get rid of it, so I'm going to wall this thing off. And so the idea is the first thing we need to do is understand these granulomas. So we've spent the past 25 years really building models to try to understand these black boxes that, for immunologists that are interested in understanding TB and how we can tilt the balance that these granulomas do the good job of actually controlling that bacterial growth. Because sometimes the bugs are so smart, those granulomas don't control, they break open and the bugs spill out, and that's called disseminate, and they can disseminate it into your airways, they can spread, and bad. So that's the sort of in lung story that's going on.
Right. So potentially, if we could figure out which of those granulomas is going to break open, so to speak, we could maybe make some predictions in terms of this person's at risk here, or that person's okay for a little bit. The granulomas are really interesting. Yeah.
Exactly.
Okay, so the whole lung simulator, I read, can reproduce activity in the lungs, the lymph nodes, the blood vessels, just like it would be a pulmonary TB, tuberculosis infection. And you explained why all of those parts matter. How did you create that in as plain language as you can?
Sure. Well, as I indicated, we have these models of granulomas, and they're very complicated models because they're capturing dynamics in both space and time. And if you're trying to use math or computer code to capture a structure, you really need the space piece and not just the time piece. We can track things going up and down over time. You can build models to do those kinds of things, but to track how it's changing in space and in time is a little bit more complicated. So to do that, we were able to use these special kinds of tools called agent-based models. And agent-based models have been around for about a decade, maybe a little longer, since 2000. So my gosh, that's 2 decades. So what these models are able to do is you can count, you can say, here's a grid where we're going to throw a bunch of cells, and we're going to give each one of those cells a name and a personality. We'll say this one's a macrophage and it was born on this day and it has these characteristics. And this one is a T cell and it was born on this day and it has these characteristics and it can behave this way. And by the way, if this T cell and this macrophage bump into each other, here's things that should happen. And those are all based on immunological data and rules that have evolved over time. And so you can watch this thing actually emerge. So we don't ever tell it to create a granuloma in the code. It just automatically creates this granuloma based on the immunological rules. So that tells us as mathematicians, this is a very stable structure. No wonder all humans form these works because it's a natural attractor that's very like this is a comfortable place for the immune system to do its thing. So that's kind of exciting that we found out that these granulomas actually, were very easy to generate once we put the right immunological rules in there. But they're very complicated. I mean, I'm talking hundred thousands of lines of code to get these things to run. If we want to then say, well, as I told you, if I cough and cough 10 bacteria, you're going to actually form 10 unique granulomas. And we have some beautiful monkey studies to show that one bug equals one granuloma in the host. So how can we capture the generation of cells in the lymph node that are coming to the lung and the formation and maybe the interaction of these multiple granulomas? So the first thing we did was we took a healthy monkey and scanned their lungs alive and digitized them, found an XYZ coordinate so we could measure them in XYZ space and put them on a grid, and we recreate the lung. And then we take our model of granuloma and we have it running in every spot where a bacteria would come in. And then we created lymph node submodels and blood submodels, and they're all linked together so that they communicate in real time as the infection unfolds. So that's just a little summary of how it works. I don't know if there's any more details you'd like.
No, that's a good summary for people who, don't know this world. It's it sounds very complicated, very interesting, very hard to do. So is your plan to test new drugs and new vaccines in the future using this model?
Yes. So currently, we've spent a lot of time at the granuloma scale thinking about how would you treat this granuloma? Just like you would think, how would you treat a tumor, right? How do you get the drugs to it? Like if it's in a strange site, a lung, a liver, a kidney, wherever you might have it, how do you get the drugs to it? Then once the drugs are there, how do you get it to penetrate into this complex 3D dense cellular structure to get to the right bugs at the right time, doing all the things? And then, so that's where we have spent probably the past decade is trying to understand treatment at the single granuloma scale. But the idea is that it's not. So one thing I failed to mention to you is that because these granuloma structures do form a barrier against treatment in some sense, just like tumors do, we treat with 4 drugs for 9 months for people that have TB. Now, most people don't finish their 10-day course of antibiotics. So it's almost crazy to imagine someone to take 4 antibiotics for 9 months. And if they're non-compliant, resistance can develop. So there's a lot of problems there. So these are all the issues we've been looking at the granuloma scale. Now we want to take those same studies and do them. Okay, we've learned a lot at what it takes to make things work at the granuloma scale. How can we make things now work at the whole, when we think about the whole lung and how things are moving through the blood and the concentrations and the pharmacokinetics, pharmacodynamics of the drugs in those locations? And so, yes, we are now currently working on, translating what we learned at that scale to the drugs. And there's about 20 TB drugs available. So we have lots of combinations and permutations of these drugs that we can test. And we have beautiful tools we've created about optimizing. So we can say, what's the optimal dose we can, give to give the least amount of drug and the shortest amount of time with the least amount of total antibiotics. And that's important too, because right now the World Health Organization, Bill and Melinda Gates Foundation, other foundations, their goal is to reduce the number of drugs and shorten the treatment time. You can imagine that is needed because it's happening in places that are developing countries where access to these kinds of things are limited. So there's a big push to kind of reduce the number of drugs and the time of treatment. So that's what our goal is now. And the same sort of things I just described to you about drugs, we're also doing for vaccines.
So these would be the virtual clinical trials that you're working on?
Yes, exactly right.
Okay, very, very interesting. Now, and you're working with the NIH as well, or they're
Yes.
Okay. And
we work with
Gates.
the Gates Foundation, the NIH, and also there's a group in England called the Wellcome Trust. And the Wellcome Trust is almost kind of like the Bill and Melinda Gates Foundation in the US. They're a very big philanthropy company that nonprofit, but they rarely give money outside the US. I mean, outside the UK, and they have now had a new call happened 2 years ago called the Delta Leap, where they want to make leaps in very big diseases. And so they picked TB, and our group was one of 3 tuberculosis groups funded. The other 2 were in South Africa, and then there were 2 other diseases also studied under that leap. And so this has been really exciting to have kind of a global perspective, and a lot of people providing data. So the groups in South Africa are providing human data. The group in Pittsburgh is providing non-human primate data. So we're able to really build and make good predictions, and then test those predictions in the monkeys. And we've been doing that with our collaborator, Joanne Flynn, for about 22 years. We have a great relationship and collaboration going on there. So that's been really wonderful.
Wow. I mean, it's really interesting because we're so used to tuberculosis because it's such an old disease that people don't really realize that there's this great need, Yeah.
Exactly. And I think if I talk to people about TB, most people say, well, isn't that eradicated? I mean, that's their first,
Mhm.
kind of like smallpox or polio.
Yeah.
People think that those things are gone, but in fact, that may be true in the US to some extent, but it's
Yeah.
not true globally. And we are
Yeah.
seeing a rise all over the US in TB, COVID co-infections, HIV co-infections, immunosuppression, all of these things, have
Yeah.
helped.
I know. And we just saw polio recently, I guess, in New York. Yeah.
Right.
But yeah, we do have this, this vision of, oh, that's an old disease. We don't have to worry about it. I wanted to ask you 2 more questions here. Now, you plan to hopefully one day make a whole virtual human model, not
Yeah.
just wow, that sounds complicated.
I agree. And I don't intend to do it alone. A lot of times the new lingo for that is called a digital twin. And there's actually a group at the University of Florida run by Reinhard Laubenbacher. And he's actually having a conference in February where that's all we're going to discuss is creating a digital twin. And the idea is that people like me have been studying pulmonary disease for a while, but other people have been studying heart or brain models or kidney models or liver models, or even reproductive organs. And our thinking is that if we could in some way connect all of these models and get the expertise of all the groups together, that we could indeed create a digital twin or a virtual human that we could not just test pulmonary diseases like we can for the lung model we've created, but all diseases, and also non-infectious versus infectious, because things like cancer, diabetes, heart disease, are not infectious diseases, which is what we've focused on. So we would hope that would be a good long-term goal, and potentially within the next decade or 2, that is something that's definitely tangible, given the right support financially and computational, because these things are very computationally expensive. So to do something like that would require, national buy-in for
Funding,
supercomputers
lots
and
of funding.
yeah,
Yeah.
lots of funding. Yeah,
Always comes
and
down to funding, money.
doesn't it? Yeah.
Yes, it really does. To get something off the ground, it really does. And just from these virtual clinical trials you're doing, when could we expect, publication of some of these results? Is it a way off, close in the near future?
Well, that's a good question. So we published a lot of the studies with the granuloma scale drug already. Next year, we should have a study out with that we're working on now for using HostSim, the host simulator model, which is the whole lung model, to with the drug treatments to optimize which drugs are available. So we've got some beautiful results on that we're excited to share next year. So we think that within a year you should see those data.
Interesting, very interesting. Well, thank you so much, Dr. Kirschner. I appreciate you joining us. Thank you to our viewers. Tell us in the comments what you thought about that. Some cutting edge, cool stuff here. So thank you for your time. Appreciate it.
Thank you.
And we'll see you here next time on the Trial Site News podcast. Have a good day, everyone.